Welcome to Ones and Zeros. My name's Ben, and today we are going to be taking a look at episode 3 of our FPGA Basics series. In this episode, we're going to be taking a bit of a look at clocks and sort of seeing a little bit about how they're used and how we can actually manipulate clocks to use them in some different ways, and that'll also allow us to introduce a couple of different things with the Verilog HDL that we haven't done in previous episodes, and get to sort of expand upon some techniques that we have used in previous episodes as well. So what we're going to do first up is we are going to be using the same FPGA board that we've been using so far, which is the Terasic D0CV board, which we've got there. I have actually taken the bit of perspex off the top of that one for the moment, just because it films a little bit better without that having light reflecting off it. But that's the one we will be using. I do have a microcontroller board sitting off to the left of that as well, which I'll explain in a little bit. But basically, like I said, we're going to take a bit of a look at dealing with clocks and how they sort of come into working with FPGAs. So at the moment, the purpose of the microcontroller is to supply a low-speed clock to the FPGA. And the reason why we're doing that is because we could use the 50 megahertz onboard crystal that's on the development board. However, I would like to look at doing PLLs and stuff in a future video, and 50 megahertz is a bit quick to show some of the stuff as far as a simple demonstration. So effectively at the moment I've got the microcontroller board just supplying a 4 hertz clock, which we can see what that looks like if I just jump over to the oscilloscope. So we can see down the bottom of the oscilloscope, it's letting us know that we've got a 4 hertz frequency, and it's basically just a continuous square wave. So that's what basically all clock signals are going to look like. It just depends on the actual frequency that they're operating at. So in this case, a nice slow one, just so that we can sort of get a bit of a feel for it, like I said. So there's a couple of important things that we need to be aware of when we're dealing with clocks with FPGAs, and that's as far as the actual clock edges or the rising and falling edges of the clocks. So if I jump over to this one, we can draw a bit of a diagram. So if we've got, see how neat I can actually make this. If we've got our clock signal, again, just continuous, it'll just keep going. Our frequency is going to be determined by how long each cycle of the clock is. So the full cycle, the high part when it's a binary 1 and the low part when it's a binary 0. So that'll typically be something that's measured in time, and in the case of the particular clock that we're using here, that overall time is 125 milliseconds. Actually, no, that's 250 milliseconds. It's 125 per. Let's just fix that up. So that's 250 milliseconds in the case of the clock that we're using at the moment. Now, as I was talking about with the clock edges, so we're going to have this edge here, which is the transition from low to high, which is a rising edge. Apologies for my writing. Or we will also see it listed as a positive edge when we're dealing with the FPGAs. And then we've got the other edge over here, which is when it transitions from a high to a low. And this is our falling edge or our negative edge. And those terms are pretty much interchangeable. So falling edge or negative edge is basically the same thing, much as with a rising edge or a positive edge. It's basically the same thing. So that's what we actually use to determine how the clock is going to trigger things to happen in the FPGA. So we're going to be triggering some things on the rising edges and some things on the falling edges, or the negative and positive edges respectively. So let's get stuck into actually doing something with that and see how that kind of works when we're dealing with the FPGA itself. So we'll jump over to Quartus Prime Lite, which we've got running there, and make sure I pull up the other bits I'm going to need here as well. And I haven't actually set up a basic project for this just yet. That way, even though I kind of showed it in the first episode, you'll be able to see how I go about getting the project set up with only the bits and pieces that we need. So we're going to create a directory for this. Just create a temporary one on our desktop for the moment. And I will pop this little bit of code that we're creating today. I'll pop the Verilog file up onto GitHub as well and pop a link in the comments just in case anyone wants to check that out, just because it is a little bit more complex than some of the stuff we've done previously. But we're going to go through it all fairly slowly so that we're just looking at each piece in turn and getting a feel for how each bit sort of works. Let's just call it episode 3 clocks. So just picking out a folder and a name for that project. We want an empty project, don't want to add any files to it. We're going to go to board and we're going to select our DE0CV board from there. That way it's going to go through and set up all the I/O and everything for us. We're not going to worry about any of these settings in here. Again, we're just doing something fairly simple for the moment. And we can just click on finish and it's going to go through and get that project created for us. Wait for that to finish doing what it's doing. There we go. All right. Now over on our project navigator, we're just going to chuck it over to files and we'll see all of the files it's created for this project, which we're going to get rid of. We're going to create a new Verilog HDL file, which is going to contain the code that we want for this video. And we're going to go through and copy all of our input and output layout from one of our previous projects, just because that way it's all ready to go. Like so. We could go with our main file that it has actually created for us if we wanted to, which is this one here. And we could go through and actually clean it up. It does have the inputs and outputs and everything set up here, but I just find going with the template that I've created previously tends to be a little bit neater and easier to follow. So currently the 20th of January, this month's going past pretty quickly. And we're going to save this file and we're going to save it the same as this module. Due to the fact that that will be the top level module or the main module of the project. And the next episode of the FPGA basic series, we're actually going to go through and look at what modules are and how they work and all of that sort of stuff. So that's why we're naming it that, but again, I'll explain that a little bit further in the next video. We're just going to go through and delete the rest of the video, rest of the files that are in here at the moment, just so that the only one we've got there is our QA main.v, and then we're going to right click that and go set as top level entity and just save that file, and that is all set up and ready. We can change this back to hierarchy. And we can see that the first, or the main module in our hierarchy is now our QA main module. like so. Excellent. All right, so that part's out of the road. Let's get into actually doing a little bit of stuff with this. Now, the first thing I'd like to do is if we just go start playing with stuff now, the 7-segment displays that are on the board will all light up because basically each segment on those displays requires a binary 1 to turn it off, and by default the signals that are going to them are going to be binary zeros. So just so that they're all turned off and not distracting us from what we're seeing on the normal LEDs, we're just going to go through and assign all binary 1s to these guys just to turn all of them off. So for each of these, if we go up to here, we can see each of those has 7 signals going to it, 1 for each segment. So we're just sending it basically 7 1s. So there's single binary 1 to each of those signals. We could also write this as like so. So basically telling it we have a 7-bit number that we're giving it. In this case, the B represents it being a binary number, and then the 7 1s for the binary number. Or we can save ourselves a few keystrokes and just do it in hexadecimal, which 7 1s in binary is 7F in hexadecimal. So basically do the same thing. Again, just saves us having to type quite as much. Now, there's 2 clock sources that we're going to use in this video. One of them is the clock that I mentioned that we've got coming from the microcontroller, our 4 Hz clock signal. And the other one is going to be a manual clock input, which is triggered by us just pressing one of the buttons on the development board. So with that, we're going to create a couple of wires that represent those signals. So a wire in Verilog is essentially like a wire when you're doing electronics. It's something that allows you to connect one thing to another thing, or in the case of Verilog, you can connect multiple things together, but think of it like what it's called, which is a wire. It's basically just going to allow us to connect some stuff together. And it can make it a little bit easier to be able to see what's going on when you're going through the code as well. So the way we create one of those is similar to what we're doing when we do a register. We just tell it it's a wire. It's only going to be 1 bit wide, so just a single signal. So we don't need to tell it what size it is. And I'll sort of explain it a little bit more as the video goes on as well with that. So we're going to have our clock auto input. So we're going to call the clock coming from the microcontroller the automatic clock. And we've got that connected up to GPIO 0, pin number 0. So if we go up to GPIO 0, we've got 36 different pins. And those are these guys on the board. So this one here is GPIO 0, and then this one over here is GPIO 1, and they've all got a bunch of 36 signal pins as well as some VCCs and grounds. So in order to connect the microcontroller up to it, the white wire there is basically just our clock signal, and then we also need to connect the grounds between the 2 boards, which is the black wire that you can kind of see there, which is going over to one of the grounds here. And that allows us to get the signal over to that. So if we jump back to this one, go back down to here. So basically this just allows us to have a wire which we've given a more relevant name to, so clock auto input, rather than having to type GPIO 0 with the 0 in brackets when we go to use that. And when we go to look through the code, rather than having to try and figure out what GPIO 0 is, we'll be seeing the name clock auto input instead. And then we're going to have our clock manual input, which is going to be connected up to one of the buttons, which will be key 0, which jump back to our board. We can see that's this guy just here. And I might move that over a little bit just because we're going to be wanting to see the reset button there as well, which is that little guy there. So key 0 is going to be our manual clock input, and then we've got our automatic input coming from the microcontroller over there. Excellent. All right, so with the with the push buttons on that development board, they are active low signals. So when you're not pushing it, it's going to be giving us a binary 1. When you push it, it'll give us a binary 0. And for what we want to do, we actually want that flipped around. We want it high when we're pushing it, which is why we put the little tilde symbol in front of key 0, just to invert that. So even though key 0 is a active low signal, because we're inverting it, our clock manual input signal is actually active high signal. So just to make that a little bit more convenient when we go through and do that. Now the next thing we're going to do is kind of building on some of what we had a look at in the last video when we were looking at registers. So in order to allow us to select between some different clock speeds, we're going to add a couple of elements there, and I'll explain how they work as we go. But the first thing we're going to do is have a register that is basically a counter. So it's going to increment up by 1 each time the automatic clock triggers. So we're going to basically get it almost like a counter, effectively. So similar to what we were doing when we were using the buttons to be able to increment or decrement the value in the register during the previous episode. So we're going to call this the clock prescaler counter, and we'll actually see why it's getting given that name when we get a bit of a demonstration from it. It'll make a little bit more sense. Now, I'm going to want this to have 3 bits, so it'll be a 3-bit register, so bit 2 through to bit 0. And we're going to call this clock prescaler counter register. And our default value that we're going to put in there will be 3 bits. It'll be put in a binary value and just 3 zeros, so that it's filled with all zeros by default. Now, in order to trigger that counter to actually count for us, we're going to use an always statement with the @ symbol. And I'm going to say always on positive edge, which is going back to what we're saying about the clock edges before. So saying we want it to trigger something whenever our clock auto input goes from low to high. And we're also going to have it so that it will, actually no, we'll leave it as is with that. So we'll just trigger it on that one, keep it simple. And then we'll just go begin and end. So basically anything that we put inside this begin and end is going to happen whenever our clock coming from our microcontroller goes from a low state to a high state. And we could also, if we wanted to trigger on the opposite edge, we could go negative edge on that, and then it would trigger whenever the clock goes from the high state to the low state. Right, we're going to go with positive edge on that one, and we're just going to tell it that every time that clock transitions from low to high, we're going to increment our clock prescaler counter register. Now, although we use a equal sign outside of our always statement, when we're going to do something that's based on an actual clock signal, we use the assignment operator that has the less than symbol and the equal sign. And we're just going to go clock prescaler counter register equals clock prescaler counter register plus 3B001. So it's basically just adding a 1 to it. We could just put a 1 in there, that would do the same thing. I prefer to do it like that because that's letting us know that we're adding a 3-bit value to it, and it also is consistent with the way we're putting a value in the register up here. So again, it just keeps the code a little bit cleaner, and I find it makes it a little bit easier to be able to understand what it's trying to say. Now, we're going to create another wire. This time, rather than just having a single signal, it's going to be 4 signals. So similar to how we create a register that has 3 bits, we're going to create a wire that has 4 bits. So we're going to go 3:0 so that it knows it's 4 bits. And we're going to call this clock prescaler counter. And we can actually pack multiple signals into a larger signal. So in this case, what we're going to do is we're going to take our 3-bit clock prescaler counter register, like so, and that'll fill up bits 3 through to 1 of our wire here, but we'll have bit 0's got nothing in it at the moment. So we also want to put in our clock auto input, and that will make sense a little bit more in a moment. Now, we don't necessarily have to tell it that we want bits 2 through to 0 here. If we want all of the bits that are in that register, we can just go like that and it will automatically go, okay, you want all of the bits in there, so that's going to be 3, and then we're adding an extra bit to that. So that gives us a wire that's going to have 4 bits worth of width, or 4 individual signals side by side. Now, so that we can see what that's actually going to give us, we're going to send that out to our LEDs. So we're going to assign LED R3:0 because we want LEDs 3, 2, 1, and 0 to display the 4 signals we've got on our wire. And we're just going to tell it that we're assigning to that the clock prescaler count that we've got there. Now, this might seem a little bit confusing why we're actually doing this at the moment, but when you actually see what it does when we put it on the board, it's going to make a lot more sense. It's actually quite a useful trick that we're using here in order to give us clocks of varying speeds, basically. So just waiting for that to compile for us. Do, however, have an error. Where do we have an error? Ah, okay. I forgot to tell it that that's actually a hexadecimal number rather than a binary number, so we'll change that to a H. No other errors there. Let's compile that again. So you can, in the console, you can actually double click on the error messages as I did there, and it will take you to where that error message is. Some of the error messages might take a little bit of practice to figure out what it's saying, but as you might have seen with that particular error message, it was basically just saying there was an illegal character in the value, so it's fairly self-explanatory. So it's going through and doing the fitter stage now, where it's figuring out how it's going to fit our design into the particular resources in the FPGA. All right, that's that stage done. Just about. Okay, onto the assembler stage. So it's creating the bit stream that actually configures the FPGA based on how the fitter determined it needs to be configured. And then just doing a bit of timing analysis to figure out how fast different aspects of the design can run. And that should finish in a second. Excellent. All right. So we'll pop that onto our device, grab our SOF file and tell it to start programming that one. Jump over to our board. And we can see that we've got 4 signals that are operating at different speeds. So our rightmost signal is the signal that is coming directly from our microcontroller. So unmodified, that's the same signal that we're using to clock our counter. And we can see that that's operating at the 4 Hz, so flashing 4 times a second. The next LED across is bit 0 of our counter that we created. And we can see that because that's counting up every time it gets a positive edge from the clock, it's actually flashing on and off at half of the speed as to what the 4 Hz clock is. So that's giving us a 2 Hz clock. And then because of the way binary counting works, when it's incrementing by 1 each time, our bit 1 of our counter, which is the next one across, is then operating at half the speed again. So that's giving us a 1 Hz clock, or 1 cycle per second. And then finally, this 4th one is bit 2 of our counter, which is giving us a 2 Hz, half a Hertz, signal. So it's flashing on and off once every 2 seconds. So just by using the counter, we're able to generate some clock speeds that are lower than our initial clock is running at, which is why we go with the term of Prescaler, because it's actually scaling down the clock speed in order to give us a slower speed. So that's why we went with the name of Prescaler, and that's kind of why we went and created a counter, because we're going to set it up so that we can actually select between one of these 4 different speeds for a particular clock signal that we could then use for something else. So that's kind of how that works. And if we jump back to go with this camera view and close our programmer, get rid of that, and we can see when we created this wire, we've got the 3 bits of our counter register, which match up with the 3 left-hand most LEDs that are going on and off, and then our right-hand one, which is the actual clock that's coming straight from our microcontroller. So I hope that kind of makes sense. So simple pieces, but starting to create something that's a little bit more complex from that. And that gives us a bit of an idea of how we actually go about using wires, either to carry a single signal or using wires to carry multiple signals, and also being able to pack different signal sources in. So in this case, a 3-bit register and a single bit clock input into a 4-bit wire, so that we can then output that 4-bit wire to our LEDs just like that. So on to our next stage. And we're just going to comment out where we're assigning that to our LEDs for the moment. Jump back to that view there. So the next thing we're going to create is a thing called a barrel shifter. And what a barrel shifter is, we'll jump over to this one, is basically something that allows us to shift bits in a particular way, left or right. So if we have a 4-bit value, say for argument's sake we had 1 0 0 0 in our 4 bits, our barrel shifter allows us to shift the bits left and right, and the bit on the end that kind of falls off wraps around and goes to the opposite end. So say if we were to take this particular value and we wanted to barrel shift it 1 bit to the right, then we would have our output value here, so our 4 bits that we're putting the number into. We take this bit, we move it 1 bit to the right. We take this bit, move it 1 bit to the right. Same with this one. This one here would get thrown away in certain types of shifters, but because we're using a barrel shifter, it's going to get wrapped around and put into the leftmost bit. So the value that we would then get out is 0, 1, 0, 0. And similar in a situation where we were shifting to the left, where we've got our input and our output. And we'll go with the same value, 1, 0, 0, 0. In this case, we'd be shifting this bit to the left 1, this bit to the left 1, this bit to the left 1, and then our leftmost bit gets shifted over to our rightmost section. So that would give us 0, 0, 0, 1. So that's kind of what a barrel shifter does. And it's going to be used to help us select which clock we want to have, depending on how fast we want the clock running, based on the fact that we've got 4 different speeds of clock signal available to us from the counter that we've created. So let's get rid of that. And I'm going to call this our clock prescaler selector. And we'll create a register for that. This one's going to contain 4 bits. So bit 3 down to bit 0. And we're going to call this our clock prescaler selector register. And we're going to fill it with a default value of 1000, similar to what I did in the diagram just now. So we're going to create another wire, which we're going to call clock prescaler select faster, which we're going to take the signal from one of our push buttons, so push button number 2. And similar to what we did with our clock manual input up here, we're going to invert that so that it becomes an active high signal rather than active low. And then we're going to do another one, which we'll call clock prescaler select slower. And this will be using push button number 3. So what those 2 push buttons are going to allow us to do is either select a faster or a slower clock speed based on the 4 clock speeds that we have available. So in order to do that, the way it's going to do that is by taking our clock prescaler selector register and shifting it 1 bit to the left or 1 bit to the right each time it pulses while we're holding down either push button 2 or push button 3. So because we're only putting a single 1 in there and 3 zeros, that 1 is effectively going to move around left or right as we shift it. And we'll have a look at how that works on the LEDs as well, so if that's a little bit confusing at the moment. Now with this one, we are going to have an always statement that triggers from 2 sources. So we're going to have it trigger from the negative edge of our reset end signal, which is the reset button that we've got on the board. So that way we can actually use that to be able to reset our selector register anytime we hit the reset button, so it goes back to its default value. And the reset signal is actually an active low signal, which is why we're triggering on the negative edge, because it's normally high, but when we push the button it goes low, and as a result we want it to trigger when that high to low transition happens. So I'm going to go negative edge of reset N or the positive edge of our clock auto input, which is our clock that's coming from the microcontroller. Make sure I use the right bracket in there. Almost went to type C++ there for a second. Alright, so that's the always statement for that one. So similar to the always statement that we used up here, with the exception that we've actually got 2 sources, the negative edge of our reset signal and the positive edge of our clock. Now in here, we're going to firstly worry about what happens if we're pushing the reset button. So we're going to go if not reset N, so if the reset button's being pushed, then we want clock prescaler selector register to be filled with our 1000 value, which is its default value. So anytime we press the reset button, it's going to fill that value in for us. Now, if we're holding down the faster button, or button number 2, when we get a positive edge from our auto clock, then it's going to go through and shift the register, do a barrel shift 1 bit to the right. So in order to do that, we're going to go if clock prescaler select faster begin, and we might pop an else in there as well because we want that to carry on from that same if statement. Now we could have just put in key 2 like that with the invert symbol to make it active high. However, in order to make it a little bit more readable and understand what we're actually putting in there, that's why we create the wire with clock's prescaler select faster, and then we can use that name in here so that when we're looking through this bit of code, it actually makes more sense of what we're actually trying to accomplish there. That can make it a little bit easier to find bugs, and doing it this way and putting a wire in there is not actually going to make it more complicated as far as how it's going to use the resources on the FPGA. So again, little things like that can make it much easier to go through and try and figure out if something's not working quite right. So in here, we're going to do the barrel shift. So clock prescaler selector register, and our make sure I get this right. So our bit 0, which will be on the right hand side, will get shifted all the way to the left, and then our other 3 bits will be moved over 1 bit to the right. So doing a barrel shift 1 bit to the right. So our leftmost bit is going to be clock prescaler select register bit 0, followed by clock prescaler select register bits 3 down to 1. So moving our rightmost bit over to the leftmost position, and then shifting the other 3 bits over to the right by 1 bit. So again, using that, being able to pack values together in order to make that happen for us. So we'll call that faster, and this one will be slower. And in this case, we're going to do the same thing, except we'll do a barrel shift 1 bit to the left. And again, we'll get to see how this actually looks on the LED, so it makes a little bit more sense as well. So clock prescaler selector register, and in this case we want to take our leftmost bits are going to be bits 2 through to 0 because they all get shifted to the left. Select register 2 through to 0, and then our what was our leftmost bit is going to get shifted all the way to the right. So that will be bit number 3 is then going to go all the way over to the right hand position here. And that's basically how that barrel shifter works, and it'll make a little bit more sense why we're actually creating that as we go on to the next step as well. But just so that we can see how that actually functions, let's send the 4 bits of that register out to the LEDs and have a look at how that actually works. Like so. Let's compile that. we've got an error. And as I mentioned before, we can select one of the errors, double click on it, and it's going to take us to where the particular error is. I'm guessing it's going to be a spelling mistake. That should be select or register. Like so. That looks a bit better. Let's compile that again. And the next stage, after we have a look at how our barrel shifter works, we're going to see how we can take the barrel shifter register and our 4 clock signals and blend those together in order to give us the ability to select one of those 4 individual clock signals. Key to that being the fact that our barrel shifter has 4 bits and only one of those bits has a 1 in it. All the other 3 bits are all zeros. So by combining the value in the barrel shifter with the 4 clock signals that we've got, we can actually use it to select one of those 4. And again, that will make a little bit more sense when we actually see how that works as well. And a lot of these particular concepts that we're using are the very concepts that you use and build up from in order to start to create much more complex bits and pieces. Headphones messing with my hair again. Excellent. So we've got that over onto the board. No, we've compiled it. We haven't programmed it. So let's do that. The coffee is not working tonight. So we'll grab our SOF file, pop that over onto our board. We can see the lights change on the board there to let us know it's programming. And we can see our default value. So if we just take into account these 4 rightmost LEDs, and the value that we put into that selector register was 1000, and we've got 1000 bit up there. Now we set up our key 3 or button 3 and button 2 to be able to shift that value right or left. So if I press the right one, it's going to shift that one over to the right, and then it'll wrap back around and keep going every time we press that. And then the left-hand one will actually shift that to the left. And because that's being clocked by the signal coming from the microcontroller, if we hold down the button, it'll just scroll through that and just keep shifting that value around whichever direction we tell it to go. So that's how the barrel shifter works. And that would work regardless of what value we wanted to put in there or how many bits wide we wanted to make the barrel shifter. That concept works there as well. Something that you could use if you wanted to do barrel shifting within a CPU in an arithmetic logic unit or something like that, which is also something that we'll look at in future. So that's our barrel shifter. And again, using the way clocks work to trigger that barrel shifter as well. It's both our reset signal and our buttons. And if we switch back over to the board as well, if we change this value and we hit the reset button, we can see that that fills it back with the default value as well, regardless of what value is currently in it. And it happens immediately when we press that because of the fact that we told it that we want to trigger this statement on the negative edge of the reset signal. So it'll trigger on that, or it'll trigger on our normal clock signal regardless. So that's that one. And let's actually set it up. So we're nearly done with what we're going to have a look at today. Just do the last little bit now. And we're going to call this section of the code our clock selector. And I'm going to create a wire. We're going to call it clock prescaled. So it's going to be the overall signal coming out of our clock prescaler. And what we're going to do is we're actually going to go clock prescaler counter and clock prescaler selector register, and check if that doesn't equal a 4-bit 0 value. So it's going to take the 4 bits that we've got in this wire, so our 4 different speed clock signals. It's going to AND those together with the 4-bit value that we've got in our selector register. And because only one of those bits in the selector register is going to be a 1 at any point in time, then it means that only one of the actual clock signals can come out at any particular time, depending on which of the bits in the selector register has a 1 in it. So if it's the leftmost bit, then it's going to give us the slowest clock. If it's the rightmost bit, it's going to give us the fastest clock, or one of the ones in between. So that's what that AND statement will do. And then by checking whether it is not equal to 0, then allows us to turn that into a single 1-bit value that will actually contain the clock signal that we're looking for. Now, I mentioned at the start, we also want to be able to have it so that we can choose to have a manual clock where we can manually pulse it with a button if we want to do that as well. So we're going to have one of the switches on the board, which is we're going to use to allow us to select whether we want the automatic clock at whichever speed we've selected, or if we want it to be a manual clock where it'll pulse whenever we push the, button number 0 on the board. So we're going to use switch 0 for that one, which is one of the switches underneath the LEDs. I'm going to create another wire, which we're going to call clock auto, and that is going to be clock select and clock prescaled. So basically means that if our clock select here is a binary 1, then it's going to allow our prescaled signal through. And then we're going to call another one, which is clock manual. And we're going to go the inverse of clock select. So when it's the opposite option, and that will be clock manual input. Like so. So that when the switch is in the binary 0, this will invert it, which will become a binary 1, and then it's then going to allow our manual input through. And then we can create another wire, which is our overall clock signal, and just go clock auto or clock manual. So just ORing together this wire and this wire, so that regardless of which one of those is selected, that's the one that's going to end up on our clock signal. So ORs are really good for blending signals together, whereas ANDs are really good for being able to select particular signals, which is why we're going with those approaches there. And then, so that we can actually see the output of that, as well as see what we've got selected and whether we're in auto or manual mode, we're going to use our LEDs as we've been doing there. And we've got 10 of those LEDs, so let's make it so that the leftmost LED contains our actual clock signal. Then let's make it so that the next LED has our clock select signal, so it tells us whether we're selecting between the automatic or the manual clock. And then we might make it so that our prescaler selector register goes in the 4 rightmost bits. So we need to, because we've got 10 LEDs, this will be LED 9, LED 8, and if we want to put the selector register all the way over to the right, then we're going to need to put 4 blank bits in there like that, and then we can just go clock prescaler selector register, which we can put our 3:0 in there to let it know that we want those bits, but because it is just a 4-bit value anyway, we don't necessarily have to. Sometimes you might find that you prefer putting it in there. It's not going to make too much difference. However, that would allow you to see at a glance how many bits that particular signal has. I don't tend to worry about it for a single bit signal like that. You could just put a 0 in there, but you could just leave it as is and assume that that's a single bit signal that way as well. So this allows us to provide a signal to all 10 of our LEDs really easily. So our clock signal, clock select signal, 4 blank ones, and then the 4 bits from our selector register. And that will allow us to choose between some different speeds of clock or clock it manually. And this clock signal here, which we're outputting, could then be used to control other aspects of whatever you're building with the FPGA. So this allows us to not only see how we use clocks, but how we can also manipulate them to get different speeds and things like that, use prescalers. And if you've used microcontrollers where you're setting up clocks and you've got to deal with prescalers and stuff as well, that's typically how they're going to deal with it. They're going to use a counter and a selector mechanism to allow you to select a prescaled clock. What have I messed up here? Clock prescaler counter. Oh, that should be counter there. I've misspelled it up there. And clock prescaler selector register. Ah, okay. That should be clock prescaler selector reg. That should compile. Unless I've messed something else up as well. So bugs happen. Now, the other thing I'd probably recommend too when you're dealing with FPGAs, or at least what I find using this software and the Altera Cyclone FPGAs that I use, if the compiler provides you with hints, it's worth double checking the hints. Whereas in C or C++, I will in certain cases ignore them. I normally pay a bit more attention to warnings when I'm compiling stuff for the FPGA, just because it can catch certain things that you may not have noticed that can be the key between something actually working or not working. So it's worth having a look at those if you get any. Just doing timing analysis. And we can see only using 6 of the adaptive logic modules out of the 18,500 that we have. It's only using 8 registers, which is not very many considering how many we have available. And of our other resources, not using any of that either. So even though it's a little bit more complex than what we've looked at so far, it's not that much more complex in terms of the amount of resources it's actually using in the FPGA. There's also certain best practices and things with clocks that I haven't followed in this video just to keep things a little bit simpler, which are things that we will cover moving forward. The particular approach we've taken works perfectly fine for clocks that are operating at a slow speed like the ones we're using, where the fastest clock is 4 Hertz. So we can see from our 4 LEDs on the right, we've got our slowest clock speed selected. this LED's lit up, which is letting us know that we've got our switch here in the automatic position. We turn it to manual, that turns off. And when it's in manual, we can pulse our clock signal, which is the LED on the left, just by pressing the button, which allows us to pulse it manually if we want to do that. That can be really useful if you're going through and debugging certain things within an FPGA. If we turn it back to automatic, we can see our half hertz signal, clock signal coming out. If we select a slightly faster one, we can see we've selected the next fastest clock. We've now got a 1 hertz clock coming out. Select the next one. We've now got a 2 hertz clock coming out, and select our fastest one, and we get the 4 hertz. And depending on which one we select, that's the clock signal that we're actually getting out of our leftmost LED. So it gives you a bit of an idea of how clocks work, how we can actually go about creating a prescaler, and how a barrel shifter and a counter go together to be able to allow us to do that. How we can switch between an automatic clock or a manual clock or various different clock sources just based on the position our switch is in. So I hope that's been interesting. Lastly, just before I end the video, let's have a bit of a look at the logic diagram for that one in the actual Quarter software, so we can kind of see what that looks like as well. So we'll jump back over to this view, and we'll go into our tools menu and our netlist viewers and RTL viewer. And this is the particular schematic that it's come up based on the code that we've given it. So a little bit more complex than what we've done previously, but if you follow the various signal paths through here, you'll be able to find the various different components. So over here, we've got our counter register, so our 3-bit register there. In order to do things a little bit more efficiently, it's actually split up our selector register. So we've got bits 2 through to 0 of the selector register together up here, but bit 3 is off on its own down here. And part of the reason for that is because when we press the reset button, it's putting a 1 into this bit, and it's putting zeros into the other bits of the register. So if we follow our reset end signal, which is the one coming in here, we'll see that on these 3 bits, it's connected to our clear N signal, which clears that register. But if we follow that over to here, we can see that same signal is actually going into our pre-input, which basically fills it with a 1. So that's why it split those registers up, and you might see similar things like that with various designs that you might create. And then it's just got some various multiplexers and the combinational logic that we've put in there to be able to select between various things. We've got this equals here, which is where we're actually going through and checking if when we AND together our selector register and our various clocks, and then check if that equals 0. That's what that is actually doing there. And then this addition over here is what's actually allowing our counter register to increment by 1 each time it receives a clock pulse. We can see our clock input coming in. We can see it being inverted, and then that's being sent off to various locations. So it's going into clock our Prescaler selector register. It's also being used to be able to clock our counter register as well. And rather than our reset signal actually being used as one of the clock inputs to our selector register, it's realized that it's a reset signal, and that's why it's set it up so that it operates asynchronously separate to our actual clock input to those registers. So just going into a little bit more depth about some of how it's laid that out. If that part doesn't make sense, then that's perfectly okay, because that's stuff we're going to go more into depth with in future videos. I just thought I'd throw that little bit of stuff in there. just so that you could sort of see how the code turns into an actual working circuit. So that's our clock set episode. Now, as I mentioned at the start, I will put up this particular file, this Verilog file will go up onto GitHub. So I will put a link to that one underneath the video. So if you want to check that out and have a bit of a look through it and have a bit of a mess with it, see if you can make it do different things, stuff like that, feel free to grab hold of that one, try it out. Will be free for non-commercial use, as with most of my code if you do want to use it for commercial use, which I don't expect you will with this particular bit, but just reach out and we can have a chat about that if need be. So we'll just jump back over to that view. Lastly, just want to say thank you to the people that have been watching the videos, especially this series. I've been really enjoying doing the FPGA series and looking forward to a lot of the videos that I've got planned as we move forward as well. There's a lot more coming, not just in the basic series, but in a more advanced FPGA series that we're going to take a look at as well. Thank you to all of the people that have watched, all of the people that hit like and that have subscribed to the channel. We've nearly hit 200 subscribers for the channel, which is awesome. And a massive thank you to our patrons up there, especially Luther, who is our newest patron. And thank you also to Craig. You both are helping to make the channel be able to do some more advanced stuff and keep it going and putting out content, which is really cool. If you do want to help support the channel, we do have the link, the address for the Patreon just down there. If you've got any questions, leave a comment on the video. You can also jump onto our subreddit, so r/ones and zeros. Ask a question there if you like. The GitHub is also there, which is where I'll be putting the code up, but there'll be a link in the description to that as well. And thank you very much for watching.